Hey everyone, welcome to the third lecture of the FSML seminar series. And today we are very pleased to have with us Chris Wentland. So Chris Wentland is a postdoctoral appointee at Sandia National Laboratories in the quantitative modeling and software engineering department. His work currently focuses on domain decomposition and reduced order modeling for accelerating simulations of practical fluid flows and solid dynamics problems. He is also involved in efforts studying the potential applications and impacts of stratospheric aerosol injection for geoengineering. He received his PhD in aerospace engineering from the University of Michigan and a BS in mechanical engineering from Rice University. Welcome, Chris, and today you will talk to us about domain decomposition and coupling data-driven models of fluid flows. And please take it away.
Thank you very much, Ankit, and thank you, Sahil, for inviting me to give this talk. For those of you who don't know me, I'm Chris Wentland, and it was just a couple of years ago that I was here doing my PhD in the same lab as Sahil. So it's a pleasure to be back and giving a talk about some of the work that I've been doing at Sandia since then. And so before I start, I just want to acknowledge all the folks who have contributed to this work, especially going back a decade on some of this domain decomposition work, especially Alejandro Mota, Irina Tezar, and a former postdoc, Daria. And then working on the reduced order modeling side has been Francesco Rizzi, Joshua Barnett from Stanford, and Ian Moore from Virginia Tech, have all in some way contributed to this body of work on domain decomposition and reduced order modeling. And so for those of you who are not aware of what Sandia National Laboratories does, it's a United States national laboratory whose main goal is to maintain the nuclear deterrence or nuclear weapons stockpile of the U.S., at least the non-nuclear parts of those weapons, and as well as things in national and global security like surveillance and nuclear non-proliferation, as well as energy and homeland security efforts, particularly dealing with the resilience of the grid and modernization of the grid. But I would say the vast majority of the work deals with modernizing and maintaining the nuclear deterrence stockpile. But the research that goes into maintaining and modernizing the stockpile is extremely varied in terms of the physics and means of analyzing and understanding how these different systems work together. As far as solid mechanics goes, you have a lot of extreme conditions where you're studying fracture and corrosion of solids, of these weapons in extreme environments, specifically if they were to say be dropped during transport. And when if they were to ever be used, there's a lot of thermofluid coupling going on with the structural components of that. But as far as energy and homeland security goes, there's also a lot of work being done on Arctic coastal erosion and how do we model, permafrost layers in the Arctic, and a lot of that deals with varied material models, whether that be ice, permafrost, or the ocean elements of that. And as far as fluid dynamics goes as well, you have applications in hypersonic flows for reentry vehicles. You have multi-phase flows if you're studying combustion systems that relate to modern energy systems for new types of fuels and cleaner emissions. There's also ablation and reactive flows for some of these combusting systems and reentry vehicles, and also structural coupling or aeroacoustic coupling for, say, weapons in a store on a plane or something like that. And so a lot of these developing the simulation strategies for these systems so that, obviously we can't test these nuclear deterrence systems. So simulation and modeling is a big component of how we assure the quality of these systems. And certainly simulation is a useful tool in that regards, but as I'm sure many of you are aware, there is a big trade-off in both the accuracy of your system and certainly the speed. So if you have a more accurate model, generally you're going to take a hit in terms of the computational cost of those systems. as well as how many simulations you can run exploring your design envelope of these systems, and whether or not those simulations will actually be useful in some sort of engineering design analysis. And what we found at Sandia, and I'm sure many other places, is that a lot of these pre-processing steps for these systems, particularly meshing of complex geometries, is the single biggest bottleneck in these analyses. It's usually a very tedious, labor-intensive process, ensuring that your mesh quality is right for these systems. And you can kind of see on the left is this bolted, just one bolt in an assembly, and how those contact faces meet with the surrounding sink is very complicated, and it's very difficult to ensure the quality of those meshes. And especially when you're working with different physical systems, so say these climate models where you're coupling the atmosphere, the earth, ocean, and ice, a lot of these couplings can be ad hoc or phenomenological, or in the case of contact mechanics for this bolted assembly, lacking robustness, or maybe not conserving some useful quantities like conservation of energy. And so what typically happens is, if you want to bring all of these subcomponents together, you need to have some sort of domain decomposition strategy that is dividing the physical domain and simulating the components in some very robust fashion. And so, in some instances, that decomposition is very simple. Like on the left, you have these ratchet systems where obviously each of your subcomponents, you would like to mesh those independently and not have to worry too much about how those contact surfaces are related or how they're meshed relative to each other. But in some instances, you also might have repeated instances of components of your system. Like on the right, you have this rocket combustor system where each of your fuel injectors represents a fairly similar physical contribution to the overall system. And it might be nice for you to be able to decompose each of those injectors and separately represent them using different physics models that better represent what's actually happening in those spatially local areas. And so a big goal at Sandia has been, how do we build a minimally intrusive, so requiring as few changes to your very complicated production code that is enables this robust multi-scale coupling between both the different time and spatial scales in your system, but also different components in your systems, like these bolted assemblies. And so a big effort at Sandia for about the past decade, done by my two colleagues, Irina Tezar and Alejandro Mota, has been developing what's called the Schwarz alternating method for simulating these systems. And now the Schwarz alternating method is very, very old, probably over a century old, at least theoretically. But in the simplest terms, the Schwarz alternating method follows where if you have a complex geometry, you can break it down into component, simpler subdomains. So on here you have omega 1, which is a circle, and omega 2, which is a rectangle. And you can simulate your governing PDEs on each subdomain separately. And then you will have some sort of coupling step where you transmit boundary conditions from one subdomain to the boundary on the other subdomain. And then you'll just iteratively solve on these subdomains until you reach some sort of specified convergence criteria. And in the past, this has typically been used as a preconditioner for iterative Krylov solvers. But the big leap that was taken a little under a decade ago by Alejandro Mota and Irina Tezar was to just use this as a way to simplify your discretization of very complex systems, but extending this to both dynamic systems and arbitrary and nonlinear systems, where you are, again, solving your governing nonlinear ODEs or PDEs on these separate domains, and then just specifying some sort of transmission boundary conditions. And you have theoretical guarantees that this will converge to your equivalent monolithic solution if you were to not split up this domain. And there's lots of different flavors of the Schwarz alternating method. So if you're subdomains are overlapping, you can enforce a Dirichlet boundary condition at these interfaces, gamma 1 and gamma 2. But if you are using a non-overlapping decomposition, which is typically more natural, say if you were to have a contact problem where two subsystems were just bordering each other by a contact interface, that would be a non-overlapping Schwarz interface, and generally you will enforce a alternating a Dirichlet and Neumann boundary condition. So one subdomain will transmit a Dirichlet boundary condition, and another will transmit a Neumann boundary condition to ensure convergence of your solution to the equivalent monolithic solution. Some of the results I'm going to be showing today for these fluid flow systems uses a finite volume model with Go cells. And we call that non-overlapping because the physical domains don't overlap with each other. But those overlapping Go cells implies an overlap, and so it still permits a Dirichlet coupling. But overall, this formulation is minimally intrusive. You have a question?
Yeah. Do you want me to ask at the end, or is it okay if I ask now?
Probably fine to just jump in.
Okay. Yeah. So here you say in the overlapping case, we apply a Dirichlet boundary condition on gamma 2 and gamma 1, right?
Correct.
But what about the interior nodes where there's an overlap? What happens then?
Those are just redundant calculations, effectively. And so, is your thing dying? They're effectively redundant calculations,
Right.
But they're necessary for solving your PD on a subdomain, right? So those are still required in whatever residual solve you're doing, but you basically have to repeat them in each subdomain. But you're only transmitting the boundary conditions.
I see. So I am much more familiar with non-conforming meshes where we have like hanging nodes. Is it something similar where we apply constraints to make sure that they do give us physically reasonable results?
I mean, you'll have to have some sort of guarantees of your mesh quality in the interior, but you can have arbitrarily non-uniform meshes in each of them, and then you'll just have some sort of projection operator to project, the solution from omega 2 onto gamma 1. And so you can think of that like in the simplest terms, just like a linear interpolation would be a projection operator.
Sure.
But you can certainly get more accurate.
So, but the nodes inside the in the bounding, the intersecting region, they are not constrained, is it?
No.
Okay.
That's the whole point, is that these subdomains can be meshed entirely independently.
Okay.
And you don't have to worry too much about what's in the other subdomains.
I see. Okay.
Yeah. So like in the case of this, bolted, you can mesh a bolt and not have to worry about what this frame's mesh is. So there's really no constraints except on your, still the constraints on your mesh quality. So the more you refine your mesh, the more accurate your solution is, but that's true in any case.
Okay, good. Thank you.
Yeah. And so again, for the past work on this, it's typically been applied in the realm of solid mechanics, and so it's been applied to statics, where you can kind of arbitrarily choose whatever your mesh topology or refinement is in each region, depending on how you care about your accuracy in that region. And so you can kind of see in this notched cylinder, you have a fairly coarse mesh around the ends where your physics are not very complicated. But then in this notch region, you have a very fine tet mesh opposed to this hex mesh that's out here. And all you need to, again, do is specify some sort of projection operator from one subdomain onto the boundary of another subdomain. But you can also couple from the microscale to the macroscale physics. So if you have some sort of specification of what your microscale structure is in this region, again, as long as the physics, your material model is consistent in the overlap region, you can just arbitrarily map the solution, so the displacements or the velocities from one subdomain to the other, and study what is happening at the microscale in this region opposed to the macroscale in these fixture regions. It's also been applied to dynamics, and so this is another bolted assembly where you can, again, generate a mesh for these bolts independent of what's occurring on the base plate of the system. So on the left is a monolithic solution where all these nodes are matching up in the contact surfaces, but on the right is this independently meshed where the bolts are meshed independently. This top plate is meshed independently, and this base plate are meshed independently. And in certain instances, this can be faster than the monolithic solutions, even though the Schwarz method is implicitly is a iterative solution, and so you have to iterate, and that increases your computational burden. But the great thing is in the pre-processing step, your meshing analyst has to do a lot less work. You don't have to worry about conformal meshes at these contact interfaces. But a lot of those man hours that are going into this process are greatly reduced. And very recently, it's been applied to contact problems where you have, this is a fairly canonical problem of two bars hitting each other. But as you can see, the meshing topology, either a hex or a tet mesh, is fairly arbitrary on your different methods, and you will generally achieve better quantities, whether that's your displacement fields or your velocity fields on these bars, but also what we see is vastly superior energy conservation compared to similar contact algorithms like Lagrange multipliers or penalty methods. And another great thing about the Schwarz method is that you can arbitrarily apply whatever time integrator you want in each of your subdomains, and you can kind of see the effects that these have on your point measurements of velocity, depending on what time integrator, whether that's an implicit or an explicit scheme or some sort of mixture of those schemes on each of those, you can tailor your solution to the needs of your application. And so what my work has been, and what my colleagues like Irina and other folks have been doing, is trying to take this methodology for the Schwarz algorithm and use it as sort of a plug-and-play framework for arbitrarily inserting whatever data-driven model you would like into these subdomains of this decomposition. And so some work has been done on neural network surrogates. My work has been primarily focused on intrusive projection-based reduced order models, which I'll go into more in a bit. And then some work that I've done with Irina and Ian Moore from Virginia Tech has been focused on operator inference reduced order models. But this plug-and-play architecture, really what we want to target is tailoring your choice of models to the physics that are happening in your region. And so if your physics are very well understood or fairly uniform, you can maybe use a data-driven model to really speed that up. But if you have a region where you're expecting some sort of fracture to happen, which is poorly represented by data-driven models, maybe you want to retain your high-fidelity finite element solution there. But yeah, so the first part of this talk, I'm going to show some of my work done around projection-based reduced order modeling. And as a brief overview, say you are given some generic nonlinear ODE for your system where Q are your governing variables. For a fluid system, you might say that's density, momentum, and energy. And F is some nonlinear function encoding the nonlinear terms or the physics of your system, including your boundary conditions, parameterized by some mu. And your system is very high dimensional at dimension n. For scalable systems, that could be millions or billions of degrees of freedom. But the way we start off with formulating our reduced order model is positing that there is some sort of approximate solution, Q tilde, that can be structured as an affine representation of an affine offset, and then some basis vectors times some generalized coordinates or modal coefficients Q hat, where Q hat is much lower dimension than your governing state, M. And the way that you choose this basis, this phi, this trial space, is lots of different ways to do that, but we choose the proper orthogonal decomposition. Other people might know it as PCA, principal component analysis. But all this is doing is you're collecting data snapshots, capital Q, from some series of simulations of your system and learning the basis that is the L2 optimal projection of those data snapshots onto a rank M subspace. And that has a very simple solution where you're just taking the SVD of your data snapshot matrix and taking the first M columns of your left singular vectors. And then when you insert that approximation into your system, you don't actually have any dimension reduction of your ODE. It's still n dimensional. And so you need to project your system by some test basis psi, and rearrange your governing equation such that you get a low dimensional ODE for your modal coefficients Q hat. And there are a lot of different ways of choosing this test basis. I would say the most popular way is Galerkin projection, where you're just choosing the test basis to be identical to the trial basis phi. But in our case, we find that the least squares Petrov-Galerkin method is much more stable and robust. But the way you compute that test basis psi is just by minimizing the fully discrete residual of your system. So after you have discretized your system in time, you minimize that with Gauss-Newton, and the equivalent the normal equations solving that least square system ends up being equivalent to a Petrov-Galerkin projection with a test basis given by this residual Jacobian times your trial basis. And so, unfortunately, for a nonlinear system or a general nonlinear system, when you are solving for this residual, that is still scaling with your full dimension n. And so in most cases, you haven't actually achieved any cost reduction relative to your full order model. And so you need some sort of method of what we call hyperreduction. So making your governing ODE independent of that full dimension n. And so there are a lot of ways to do this. We choose probably the simplest and maybe the dumbest way of doing this is collocation, where you're just minimizing the residual at a small subset of degrees of freedom ns, which is much less than your full dimension n. And the way this works is when you apply this, what we call a sampling operator S, is you're just computing the residual at some certain subselection of these points. What the resulting system looks like is you're effectively solving your system only on these blue cells for a 2D mesh. And then these orange cells are any auxiliary cells that you might be required to calculate, say, gradients or fluxes for your system. But this is what we call the sample mesh. And ideally, you are solving on a very small sample mesh such that the cost of solving your system is greatly reduced. And so how we bring this in with our Schwarz decomposition is very simple, very minimally intrusive again, is that you are decomposing your mesh with some amount of fixed overlap. We're going to restrict ourselves to uniform Cartesian meshes here, but again, you can choose an arbitrary depth of your overlap. In each of these subdomains, after simulating your monolithic solution for your training data, you're computing a POD basis for each of these separate subdomains. And then you are selecting some sample mesh on each of these subdomains. And then you're just independently solving a ROM ODE on each of these omega i's. At every step, you are transmitting the boundary conditions to its neighboring subdomains, and you are iterating until you're converging within each of your physical time steps. And so on the right is kind of a rough idea of what this might look like for a hyper-reduced ROM, where in each of your subdomains, differentiated by different colors, you are computing, you have a sample mesh, and then just ensuring that you have the solution necessary in neighboring subdomains to transmit those boundary conditions. And so to kind of demonstrate these tactics for canonical, but we like to think challenging nonlinear fluid flow systems, where you have these wave propagation phenomena that are generally hard to represent by linear subspace methods, We're going to look at the shallow water equations where we are varying this rotational Coriolis parameter mu, the 2D Burgers equations where you're varying the diffusion parameter, and the Euler equations where you're varying the initial pressure in the upper right quadrant of this Riemann problem. And so you can see what this shallow water equation is looking like, starting from a Gaussian pulse. Same thing for the Burgers equation in the center, starting from a Gaussian pulse. And then this Riemann problem where you have 4 shocks propagating through this domain for the Euler equations. And everything here is solved on a 300 by 300 mesh, first order in space and time with a finite volume method. But generally, if you're using monolithic solutions to solve these problems, you will have a difficult time with linear subspace methods because, especially for the Burgers and Riemann problem, the ability to represent these solutions, these shock solutions with a linear subspace is very inaccurate, what we like to call a high Kolmogorov n-width problem. And so again, what we're going to be doing is parametric prediction. So we're going to have 5 training simulations at varying values of, say, the Coriolis parameter for this rotational force in the shallow water equations, the diffusivity of your Burgers equation, kind of hard to see here, but the bottom one is more diffuse. And then the strength of this shock mitigated or computed by this upper right pressure in the system. And we're going to evaluate the quality of the predictive ability on 4 interpolative testing points for those parameterizations. And so just to understand what's happening in these Schwarz systems, we're going to look at first the unsampled ROM, so no hyperreduction going on quite yet. So you have the fuller monolithic solution on the left, the monolithic projection-based reduced order model in the center, and your Schwarz solution on the right, where you can see the domain interfaces marked by dashed lines. And so this is a non-overlapping interface between these different domains. And at least in the eyeball norm, what you'll see is that the Schwarz reduced order model ends up being more accurate in the long term. Fairly granular picture here on the screen, but in the eyeball norm, you get a generally lower error because for the same fixed trial basis size, because your local trial basis is better representing that local subspace or that local subdomain local space, just because you are able to optimize that basis for any local dynamics that are happening in that area, opposed to having to optimize over a global solution, which may be much more varied dynamics. And in the most extreme cases, say for this Euler case, you can actually stabilize an otherwise unstable reduced order model, where your monolithic solution is unable to accurately represent shock solutions, whereas your Schwarz ROM for a given basis size is able to accurately propagate that shock. And in the classical Schwarz literature, what you will see is that the overlapping, the amount of overlap you have between these subdomains, it should not have an effect on the quality of your equivalent solution. You should still be converging to your equivalent monolithic solution, given some sort of convergence criterion. But it will generally affect how many iterations you need to take to reach your convergence. And so on the left, or on these plots, you can see the number of Schwarz iterations per time step that are required to achieve convergence. And for the shallow water equations, varying the overlap has very little effect on that convergence. It's a smooth solution, not quite as much of a concern. But as you move to these shocked problems, such as Burgers and Euler, what you'll see is that these non-overlapping solutions require much more Schwarz iterations to achieve convergence. But in general, you're not degrading the accuracy, despite these, even in these non-overlapping Dirichlet interfaces, which goes counter to the traditional Schwarz literature, but was a nice finding for us, at least for infinite volume methods. Now, when you move to hyper-reduced ROMs, there are some nuances and some care you have to take in how you transmit these boundary conditions. And what we found is that if you don't deliberately sample your boundary, your solution, your decomposed solution will almost always be unstable. And I think that makes logical sense because if you don't know about the dynamics of the solution at these interfaces, how can you possibly transmit that information to neighboring subdomains accurately? And so we take a fairly naive approach. I would say the simplest approach, which is just to uniformly sample the boundaries of these domains or these subdomains. And so you can kind of see in the left, you're deliberately sampling, say, every fifth cell at the boundary to ensure that there is some sort of communication of information across these interfaces. You need to take a certain amount of care, though, because for a fixed budget of sample points, more frequently sampling the boundary interface will naturally draw samples away from your interior. And so you can see this instance, you're removing sample points from the interior, and which will naturally degrade the accuracy of your solution in the interior. And so it becomes this sort of balancing act of making sure that you're propagating information across interfaces, but maintaining an accurate solution at the interior. But what we find is that for these hyper-reduced ROMs, again, for the shallow water equations, we're able to maintain a stable solution and an accurate solution, even for these hyper-reduced ROMs, where you're sampling, say, only 0.5% of the domain. That should be an N. 0.5% of your domain, and able to maintain a stable and accurate solution. And even for the Burger's equation, where you have a shock, you're able to transmit that shock across these interfaces. Granted, for these shock problems, in general, you'll have to have a much denser sample mesh. So this is 3.75% of the subdomain, or of the full mesh. But that is a fairly common finding in the reduced order model literature. But again, like I said, this becomes this balancing act of how much do you sample the boundary and how much do you sample the interior. And so you can see moving from purple with sampling every 5 to blue to green, you find this sort of sweet spot of sampling the boundary enough, but not oversampling it such that you destabilize your solution. But for the Burger's equation, or for the Euler equations, you'll generally have to sample that boundary much more frequently, to the order of every other cell. And so, which is again, just a natural complication of having shocks in your system. But in general, you can find a stable, accurate, robust decomposition for these solutions. And when you're examining the computational cost, because the computational cost is, of course, what we actually care about for these reduced order models, you can look at these Pareto plots where you're measuring the error on the y-axis and the speed up relative to either your Schwarz full order model or your monolithic full order model. You'll see in this cyan and magenta plots are the Schwarz ROMs, which the magenta being the Schwarz hyper-reduced ROMs, and the equivalent monolithic solutions in blue or in red for the hyper-reduced ROMs. For a fixed trial basis size, for these smooth problems like the shallow water equations, you can generally achieve a more accurate and equivalent cost solution to the monolithic hyper-reduced ROM. But when you move to shock problems, generally you will be able to achieve a lower error than the monolithic solution, but not achieve the same amount of speed up for relative to monolithic solutions. But even with the question.
Yeah, so how is this hyper-reduced prompts giving better accuracy than your monolithic ones?
Better accuracy?
I mean, yeah, so if you look at...
So you're comparing Schwarz versus monolithic, right?
Right.
So these are the monolithic solutions. Again, it goes back to that.
Oh, so monolithic
is the global solution.
Oh,
yeah,
okay.
monolithic versus decompose is what we want to look at here. So if you have If you have a global trial basis, generally that will be less accurate for a fixed basis dimension than for the local subspace. Yeah, again, for these shock problems, you'll generally not be able to achieve the same amount of speedups. But again, the problems that we want to look at Sandia, in many instances, you have to have a decomposed solution. So again, these bolted assemblies, or if someplace you want to look at the microscale physics of these problems, it naturally incurs a decomposition. And so it's reassuring that we can still achieve maybe an order of magnitude speed up relative to the full order model short solution, which is encouraging. And so, a lot of this work, at least for these fluid flow systems, is open source through this project called Pressio, guided by Francesco Rizzi, our collaborator. And so all of this work that I just showed has to deal with intrusive ROMs, where you have to get in the guts of the code, change your source code, and futz around with these nonlinear operators. But if you have a production code that is big, or it's written in a really old language, or it's very tightly version controlled such that you can't make significant modifications to it, what people will generally turn to are non-intrusive ROMs, which you only have access to the snapshot data. You don't have any access to the source code. You basically only need the outputs of your source code. And a fairly recent, or it's been being very rapidly developed these days, is this idea of operator inference, where you are again giving some of your governing ODE. In this case, we want to focus on linear ODEs, where you have a stiffness matrix K and some boundary operator B. And you don't actually know the form of K or B, because again, you can't get into your code. But you assume that there is some sort of existence of a reduced operator where you are projecting those operators via your trial basis phi, and you can learn those approximations in this reduced space via a least squares minimization problem, where you are taking snapshots of your data Q, computing an approximation of your time integrator, and learning some sort of approximation K hat and B hat to those operators in this reduced space. So those operators K hat and B hat are only of size m by m, or in the case of the boundary operator, m by however many inputs at the boundaries you have. And so, of course, that formulation assumes that the dynamics are linear, but these can be very easily extended to polynomial nonlinearities. There has been work done on dealing with non-polynomial nonlinearities, or you can lift your system to a polynomial form by introducing additional auxiliary terms into your governing ODEs. And generally, like I said, you will approximate your time derivative Q dot with finite differences or something from your snapshot data. But the way this fits in with Schwarz is virtually identical, where you're decomposing your subdomain, you compute a POD basis on each of those subdomains, approximate your operators K hat and B hat, again, each for those subdomains, and solve this reduced operator system on each of those subdomains, and then transmit your boundary conditions via G. So again, your boundary operators are still coming into play. And I want to make a point that this is generally extensible to any other data-driven model you want to use, as long as you have some means of transmitting boundary conditions. So, we've tried to do work with pins, because you're enforcing some boundary loss in that pin minimization problem. But as long as you have some means of transmitting boundary conditions between these6subdomains, you can apply Schwarz. And so the work that was done by our intern this last summer, Ian Moore, was done on the 2D heat equations. And so first order finite element method implemented with Phoenix, and then there's a separate package by our colleague called opinf that you can get off of GitHub. And then given some of, so this is what the system looks like. You're having a fixed Dirichlet boundary condition on the bottom, and then you have some sort of sinusoidal forcing at the top and left boundaries of the system. And he looked at some different decompositions of the system, either into two vertical decomposition or this four quadrant decomposition. And these are just some stills from the system, and just as kind of a comparison between what you saw for the projection-based ROMs. The great thing about op-inf is this is purely linear operations. You're not dealing with any nonlinear operators, and so these operations are practically instantaneous, especially compared to any sort of nonlinear solver that you might have generating this data. But what the big problem is with op-inf is that the action of these boundary terms are only incorporated very loosely in these through this boundary operator b hat, and so you get instances like this center term where you don't if you don't have enough training points, in this case 40 snapshots, that learned operator will not be able to accurately transmit boundary conditions between an unstable solution at the boundaries. But in the case of if you increase the training amount, you can get a stable solution where that b hat term is accurately transmitting those boundary conditions. And again, this is another Pareto plot from the work that he did. So you can see the FOM runtime in the dash line. And even for this fairly simple system, the 2D heat equations, you can get an excellent speed up with this Schwarz op-inf decomposition. In the case that you have either in cyan or yellow, you have these two subdomains. But even in where you have 4 subdomains, you're able to achieve some modest speed ups relative to the full order model. And when you look at how the error of these systems change with the rank of your trial basis, this is the projection error. So just the error in projecting your trial or your training data onto that linear subspace, you'll see that this error goes down monotonically with respect to your trial basis M or your trial rank M, but the actual online error of running these simulations ends up decreasing to a point and then actually thresholding at a certain level. And what this kind of reveals is an inherent limitation of how much information your linear operators can actually reflect the physics of your system. And so there's some work being done, or there's a lot of work being done on how do you actually enhance the accuracy of your learned operators such that you're not limited by these thresholds. And so that's the end of the research that's been done so far, but the work that is just starting this year by a project that I'm on with Irina Cesar and a bunch of other folks at Sandia is how do we automate this whole process? How do we choose how the spatial decomposition is made? How do we choose which model we want to implement in a certain region depending on the physics occurring in that region? Or how do we adapt which model we're using depending on the time-varying solution? So, if a crack starts forming in a certain region, maybe you want to switch from a data-driven model to a full-order model. So in this instance, you can say, like, if you have your shock solution, it's starting in the top right quadrant, you want to have a full-order model there. But in the upper left and bottom right regions, you can use a projection-based ROM and an op-inf in the bottom left. But as your solution progresses, you want to change which model you're using in certain areas depending on some sort of metric of how that system is evolving. But how do you gather that data for complex systems? We want to make it scalable. We want to bring this into our production codes at Sandia. This is going to be a 3-year effort. So hopefully you guys will see some new research over the next few years. But just to wrap things up, and then we'll take questions, is Schwarz is a very simple, minimally intrusive method that is amenable to bringing these methods to your production codes. And again, you're able to bring in non-intrusive reduced order modeling methods to make this very flexible. And the projection-based ROMs, which are intrusive, they're known to work fairly well and they couple flawlessly, but there are certainly issues with cost and implementation viability. And for the opt-in FROMs, again, they're lightning fast, but there needs to be some work done on how we enforce these complicated boundary conditions for these Schwarz formulations. And again, when you want to simplify the meshing in these systems where you have very complicated meshing solutions, you can often incur significant cost savings, especially in the pre-processing step or for the analysts who are building these simulations for you before they run them. But yeah, like I said, model adaptation is in the works, and hopefully we'll be able to show some cool stuff over the next few years. So I will take any questions at this point.
Thanks, Chris. That was actually really great. So we'll first take questions from people in the room, and then we'll move online. So if anyone has any questions in the room.
I have a question. Yeah. So in the work you showed where you do the PCA to find the reduced order, the efficient basis to solve your equations in, right?
Yeah.
And so you mentioned that actually provides better accuracy than like a monolithic solution, because some of the global errors are not encountered here, if I understood your word correctly,
Yeah.
right? So my question here is like this. So if you're going to propagate a solution over time, and especially if you're working with something like a wave propagation, which is hyperbolic equations in nature, which can lead to errors propagating over time as well. Wouldn't you expect the global basis to do better, or why is it not doing better? Am I clear with my questions?
I mean, so if you for these nonlinear systems, your error will generally increase in time exponentially, right? And
Sure.
These local solutions will just generally represent your local solution better, or your local basis will represent, so you'll have less projection error or less error in your representation of the solution. And so that leads to less propagation of error in time. But you're saying, is it less accurate over the long run?
Right.
And there are instances, so not relative to the global solution, at least we have not encountered that. It's
Okay.
because we're not doing any predictions in time. So all of this is within the same time frame. And so your local basis is still getting data from the full time of your simulation.
Okay.
And so the time error is not really the issue. It's mostly the spatial error that's the concern for the accuracy of these ROMs. But there are methods that try to mitigate this time error by having a sort of dictionary of different bases that you will switch over time depending on which basis best represents your time varying solution at that instantaneous moment. But we don't implement those.
Okay. But you're doing this with finite volume, right?
Correct.
So if you have a local basis, whatever solution that can be represented that basis should also be part of the global basis, right?
No, they're not. When you compute your global basis versus your local basis, there is no guarantee that those will be, like, if you were to stitch the local bases together, they won't look anything like the global basis.
Oh, I see. Okay.
Yeah.
Okay.
Because you're solving totally different minimization problems. Because the data you use in the subdomain local is only a portion of that data, and so you're optimizing that projection error just to the data from that quadrant or from that local space. And so
I see.
Yeah, you should never expect it to converge to to be equivalent to the monolithic POD basis.
Oh, sounds good.
Yeah.
And just a small follow-up. So you take the points R, the subset of the point to compute your error, right? The S R of Y.
Oh yes, the hyperreduction. Yeah.
Sorry, the hyperreduction. So how do you choose the points in interior to the domain? Is it like randomness? Or?
Yes. So for us, it was random. There's a lot of work being done there that has been done on other ways, more locally optimal. So they're called greedy methods that select a more or a better point. So like, let's say for the Burgers equation, it'll pick, more points where this wave is traversing.
Right.
In general, we didn't find for these very simplistic problems where the wave is propagating over the entire domain.
Right.
Random sampling works just as well as these greedy methods.
Okay.
But if you look at more complicated solutions, like for let's say like this rocket combustor, you might want points that are just in the flame front or something, but you don't care about sampling down here or in the injector.
Sounds good. And can you go to the, I think slide 25 or 4, where I show the results with next one?
Error results.
Where you show the convergence with respect to the number of points you took.
You're saying this is the overlap amount.
No, not this one. Can you go to,
This is the error relative to the boundary sampling?
oh, there's a boundary sampling.
Yeah.
Okay, so why is it for the rightmost one, the green one is not monotonically decreasing?
So these, I guess I didn't explain. So this is not really this is across different parameter values.
Right.
And so the physics are inherently different.
Oh, I see. Okay.
For each of these values. And so like this is a very weak shock at this end, and this is a very strong shock. And so honestly, you would expect it to kind of look like this U shape because your data is best represented in this interpolatory regime.
Ah, I see. Okay. Yeah. Sorry, I think I missed it.
Yeah. So I forgot to say what the x-axis is here.
Thank you.
I had a question.
Yeah.
So if you go back to your second last slide where you show the automated model selection.
Yes.
So if you are trying to perform operator inference in that subdomain, wouldn't you still need like solutions over the entire monolithic domain first in order to compute the POD basis?
To train your POD basis, yes. Well, you don't need monolithic. So
okay,
if you wanted, you can do Schwarz decomposition of this with all full order models here to get your data, and then you would just train your op-amp solution just from the full order model Schwarz solution in that subdomain.
Understood.
Yeah. So this is not a training step. This is an online predictive regime. So you would still need to train using either a monolithic solution or a decomposed solution.
Okay.
Full order model. So either your find volume method or your find element, whatever.
Understood.
Yeah.
And then a second question. So I think that for these problems you showed, you're just subdividing it into these Cartesian subdomains. So I imagine that at least over here, there isn't much significance of that meshing cost being saved because
zero.
The mesh is
the mesh is very simple. Yeah.
So then do you sort of see any sort of limit where decomposing this into more domains is not, more subdomains is not really having much impact, or your performance is kind of saturating?
Yeah.
And so where's the trade-off line?
Yeah. So for the general guidance is you want to subdivide as little as possible.
I see.
Because subdividing more generally requires more Schwarz iterations to converge. So in this case, we only chose a 2x2 decomposition because that's the minimum size that's required where you have waves propagating both in the X and Y direction crossing interfaces. But in general, you want to decompose as little as possible. And so in some instances, you have that decomposition chosen for you. Like if you have a bolted assembly, obviously you mesh the bolts, you mesh the plate, whatever. But for fluid flow systems, it's not as clear. Maybe you want to decompose, again, like for that combustor, you want to decompose it into the oxidizer feed tube and then the flame region and then the post-combustion region. But like I said, you want to decompose as little as possible. Your runtime will always get worse the more you decompose.
Understood. And so I think that was also kind of visible for that heat equation where I think when you had those
exactly, yeah. So
domains, the work club time was also
exactly. So yeah, this was a 1x2 or a 2x1, and this was a 2x2. So you get faster run times the less you decompose.
okay.
Yeah, so I have a question. So if you're considering two systems, like how does this method perform in case you pass like observations instead of passing like the entire states? Can you do that? Like some partial states? Like I'm assuming all the fluid simulations, you were just like transmitting the entire states across boundaries.
Yeah. So you're saying like this is a time varying experimental data that you're getting from a coupled system.
Right. Yeah. So it's like coupled system, like you just have some observations, observables, like, and
Yeah.
then you transmit that.
So that if that would not really be a domain decomposition because you're not simulating whatever is coming from the experiment. You're just enforcing those as a boundary condition.
Okay.
And so those can factor in, like if you only have a few points, like if you have thermocouples at a few points, maybe that is what you're choosing for your boundary sample points.
Okay.
And that's what you're transmitting boundary conditions only at those few points. Whereas you might simulate whatever, like for those reentry vehicles, say you have thermocouple measurements from the ablating heat shield, but then you simulate your fluid flow system, you would select points in your fluid flow system that correspond to where your thermocouples are, and then just feed that in as a boundary condition from your experimental data.
Okay. Thanks. Are there any other questions in the room? Like, if not, like people online can either type it in the chat or like just unmute themselves.
Not all at once.
Okay. If there are like no more questions, let's just thank the speaker again.
Thank you all for joining today. We will be posting this recording soon to YouTube as well. And we'll see you all again in 2 weeks' time for the next seminar. Thanks.